Hi, Bob. I've been reviewing quantum computing papers from January 2025, and there seems to be a lot of interesting developments. I'm particularly intrigued by the work on quantum internet, human quantum-computer interaction, and practical applications. What are your thoughts on the key developments this month?
Hello, Alice. January 2025 has indeed been a productive month in quantum computing research. I'm seeing several important themes emerging. There's significant progress in quantum internet architecture and applications, practical quantum computing interfaces, error mitigation strategies for near-term devices, and interesting applications in fields like finance and automotive industries. The papers on human quantum-computer interaction are particularly timely, as we're trying to make quantum computing more accessible to non-specialists.
I noticed several papers focused on the quantum internet. The technical overview by Rode et al. Seems comprehensive, and there's also work on specific applications in the automotive industry. Could you elaborate on how these papers relate to each other and what they suggest about the timeline for quantum internet development?
Excellent observation, Alice. These three papers collectively paint a picture of quantum internet development from different angles. Rode et al.'s comprehensive technical overview in the quantum internet establishes the foundational concepts and roadmap. It's quite thorough in explaining not just the technology, but also economic and political implications. Kumar et al.'s paper on quantum internet technologies, protocols, and research challenges complements this by focusing specifically on the technical protocols and current challenges. What's particularly interesting is van der Enden's paper on automotive industry applications, which takes a more targeted approach by identifying specific use cases. They've outlined a timeline suggesting that hardware miniaturization and automation will create synergies in the short term, under 10 years, while more advanced applications like blind quantum computing for autonomous driving will be feasible in the longer term, 10+ years. Together, these papers suggest we're in a phase of identifying concrete application domains while still addressing fundamental technical challenges. The consensus seems to be that limited quantum networks with specific applications might emerge within the next decade, but a full-scale quantum internet with advanced capabilities will take longer.
That timeline perspective is helpful. Speaking of making quantum computing more accessible, I was intrigued by the paper on human quantum-computer interaction by Kim et al. They mentioned specific interface techniques for QC. How significant is this work and what problems is it trying to solve?
Kim et al.'s paper represents a significant step toward addressing one of the major barriers to quantum computing adoption: usability. The quantum computing community has been primarily focused on hardware and algorithmic advancements, often neglecting the human-computer interaction aspects. This paper is trying to bridge that gap. The authors identify several key challenges that users face: the need to convert conceptual logic into low-level quantum code, difficulties in analyzing quantum program results, and obstacles in sharing programs and results. These issues particularly affect QC beginners and domain experts who aren't quantum specialists. What makes this work notable is that it proposes concrete interaction techniques through an iterative design process. They're techniques for writing quantum codes conceptually, comparing initial and optimized programs, sharing results, and exploring quantum machines could significantly lower the barrier to entry. This research aligns with a broader trend we're seeing in January's papers, making quantum computing more practical and accessible to wider audiences. It's particularly relevant when considered alongside papers like Upadhyay et al.'s analysis of quantum computing repositories and Ramalho et al.'s work on quantum testing, which also address software engineering aspects of quantum computing.
That's fascinating. It seems like there's a growing recognition of the need for better tools and interfaces as quantum computing matures. On a different note, I noticed a couple of papers addressing quantum advantage demonstrations. Could you explain the significance of Huang's paper on designing classically difficult random quantum circuits and how it relates to practical quantum advantage?
Huang's paper addresses a critical aspect of quantum advantage demonstrations: how to design quantum circuits that are provably hard for classical computers to simulate while remaining executable on near-term quantum hardware. This is significant because demonstrating quantum advantage is a crucial milestone on the path to practical quantum computing. The paper specifically discusses the automated protocol design approach used in the Zhuangzi quantum advantage experiment. What's particularly interesting is their finding that without careful design, even increasing the number of qubits doesn't necessarily make the simulation classically intractable. They estimate that for Google's 70-qubit, 24-cycle experiment, their approach could increase the classical simulation cost by at least an order of magnitude. This work highlights an important point. Quantum advantage isn't just about having more qubits. It's about constructing circuits that exploit quantum properties in ways that classical computers struggle with. It's a sophisticated game of finding the sweet spot where circuits are complex enough to be classically hard, but simple enough to run on noisy quantum hardware. This relates to Kahn et al.'s paper on quantum advantage in trading, which demonstrates a concrete application where quantum advantage translates to practical benefits, in this case, higher-paying market Nash equilibria. Together, these papers show both the theoretical foundations and practical applications of quantum advantage, suggesting we're moving beyond proof-of-concept demonstrations toward useful applications.
I see how these papers connect now. Let's shift to quantum error mitigation and correction, which seems to be another major theme this month. Jeng et al.'s paper on demonstrating quantum error mitigation on logical qubits caught my attention. How does this approach differ from traditional quantum error correction, and what makes it significant?
Jeng et al.'s paper represents an important bridge between two traditionally separate approaches to handling quantum errors: quantum error correction, UEC, and quantum error mitigation, QEM. Traditional QEC uses redundancy by encoding logical qubits across multiple physical qubits and performing active error detection and correction. It's theoretically powerful, but resource-intensive and challenging to implement perfectly on current hardware. QEM, on the other hand, uses techniques like zero-noise extrapolation to estimate and remove the effects of noise without requiring additional qubits. What makes Jeng's work significant is that they're applying QEM techniques, specifically zero-noise extrapolation, to error correction circuits themselves. They intentionally amplify noise on physical qubits and observe how the logical error rates change, then extrapolate back to estimate what the error rate would be in a zero-noise scenario. This is a hybrid approach that acknowledges the reality that early fault-tolerant quantum computers will still have residual logical errors after correction. Their experiments show universal reduction in logical errors across various quantum circuits, including fault-tolerant circuits of repetition and surface codes. Importantly, the method remains effective as circuit depth increases. This work aligns with the perspective paper by Zimboras et al. On myths around quantum computation before full fault tolerance, which argues that we shouldn't view QEC and QEM as competing approaches, but rather as complementary techniques that can be combined. Together, these papers suggest a more nuanced path toward fault-tolerant quantum computing that leverages both correction and mitigation strategies.
That's a really interesting hybrid approach. It seems like there's a pragmatic trend of combining different techniques rather than viewing them as competing approaches. Speaking of practical applications, I noticed a paper by Osaba et al. On solving drone routing problems with quantum computing. Could you explain their hybrid approach and whether this represents a near-term practical application of quantum computing?
Osaba et al.'s paper is an excellent example of a pragmatic approach to quantum computing applications. Their Q4DR, quantum for drone routing method, is notable because it combines two different quantum paradigms: gate-based quantum computing and quantum annealing. The approach is cleverly divided into two phases: an initial clustering phase using the quantum approximate optimization algorithm, QAOA, on gate-based hardware through the Eclipse QRISP programming language, followed by a routing phase employing D-Wave's quantum annealers. This hybrid approach leverages the strengths of each paradigm for different aspects of the problem. What makes this particularly interesting for near-term applications is that they've demonstrated it on real-world use cases with practical constraints like asymmetric costs, forbidden paths, and itinerant charging points. These are genuine complications that arise in actual drone delivery scenarios. I do think this represents a viable near-term application, especially because it doesn't require fault-tolerant quantum computers. Both QAOA and quantum annealing can run on current or near-term hardware, and by combining classical preprocessing with quantum processing, they're working within the constraints of today's quantum technologies. This approach aligns with other hybrid classical quantum methods we're seeing this month, such as Minami et al.'s conditional generative quantum eigensolver and Leary et al.'s efficient online quantum circuit learning. These hybrid approaches recognize that the most practical path forward in the NISQ era is to combine classical and quantum resources strategically rather than trying to do everything on a quantum computer.
That makes sense. Leveraging the strengths of different approaches seems to be a recurring theme. I'm also curious about the papers focused on quantum chemistry, which has long been considered a promising application area. Bethel et al. Discuss quantum measurement for quantum chemistry, and Suzuha et al. Present faster quantum chemistry simulations. How significant are these advances, and what challenges do they address?
You've identified two important papers addressing different aspects of quantum chemistry simulations, which remains one of the most promising applications of quantum computing. Bethel et al.'s review on quantum measurement techniques tackles a critical bottleneck in quantum chemistry algorithms, efficiently extracting useful information from quantum states. The electronic Hamiltonian in chemistry problems decomposes into a large number of Pauli terms, traditionally requiring separate measurements for each term, a significant resource overhead. Their review comprehensively covers strategies to reduce measurement costs through grouping compatible observables, leveraging symmetries, and employing error mitigation techniques. This addresses a practical challenge that has limited the scalability of algorithms like VQE. Suzuha et al.'s paper takes a different approach by focusing on algorithmic improvements for fault-tolerant quantum chemistry simulations. They introduce a novel framework called BLISS-THC, block invariant symmetry-shifted tensor hypercontraction, that achieves tighter Hamiltonian factorizations than previous methods. Combined with their active volume compilation approach, they report a 2 orders of magnitude speedup over prior algorithms for comparable hardware. Their benchmark on the P450 molecule is particularly impressive, as it's a computationally challenging system relevant to drug design. What's significant about these papers collectively is that they address complementary challenges in quantum chemistry. Bethel's work is more relevant to near-term devices where measurement resources are limited, while Suzuha's work looks ahead to fault-tolerant quantum computing, where circuit depth and runtime become the primary concerns. Together, they demonstrate continued progress toward making quantum chemistry simulations practically useful across different quantum computing regimes.
Thank you for that explanation. I'm also seeing several papers on quantum machine learning this month. Mingyoung's paper on a new quantum algorithm for PCA, Huang's quantum graph Hamiltonian neural network, and Piperno's quantum simplicial neural networks all seem to be exploring different aspects of quantum-enhanced machine learning. How do these approaches differ from classical machine learning, and what advantages might they offer?
These 3 papers represent different facets of quantum machine learning, QML, each exploring how quantum computing might enhance specific aspects of machine learning. Mingyoung's paper on quantum PCA provides an alternative approach to the original quantum PCA algorithm. Classical PCA identifies the principal components, dominant patterns in data, by analyzing the eigenvalues and eigenvectors of the covariance matrix. The quantum version can potentially offer exponential speedups for certain datasets by directly manipulating quantum states that represent the data. Mingyoung's new approach offers improvements over the original QPCA in certain regimes and provides a new method for preparing the covariance matrix on a quantum computer. Huang's quantum graph Hamiltonian neural network, QGHNN, tackles the challenge of representing graph-structured data in quantum neural networks. By mapping graphs to the Hamiltonian of a topological quantum system, this approach creates a natural connection between graph structures and quantum states. Their experiments showed impressive performance metrics, with very low mean squared error and high cosine similarity, suggesting that quantum approaches might be particularly well suited for graph learning tasks. Piperno's quantum simplicial neural networks represent perhaps the most innovative approach, combining quantum computing with topological deep learning. While classical graph neural networks can only capture pairwise interactions, simplicial complexes can model higher-order relationships, like three-way or four-way interactions. By quantizing these models, they aim to leverage quantum mechanics for enhanced computational power when learning from complex topological data structures. The potential advantages of these quantum approaches include 1. Exponential speedups for certain mathematical operations, like in PCA. 2. Natural representation of certain data structures, like graphs, in quantum systems. 3. Ability to process higher dimensional relationships more efficiently. 4. Potential for quantum parallelism to explore multiple solution paths simultaneously. However, it's worth noting that these advantages are often problem-specific and depend on efficient quantum classical interfaces, which remains challenging. These papers represent important theoretical advances, but practical implementations that demonstrate clear quantum advantage in machine learning tasks remain an active area of research.
That's a great overview of the quantum machine learning landscape. Another area with multiple papers this month is quantum circuit design and optimization. Guo and Yang discuss efficient quantum circuit compilation, Kessin introduces a graph-based approach for quantum computing, and Hyeok et al. Explore entanglement-informed construction of variational quantum circuits. How do these approaches relate to each other, and what problems are they trying to solve?
These three papers address different aspects of the quantum circuit design challenge, which is fundamental to making quantum algorithms practical. Let me break down how they relate and the specific problems they're tackling. Guo and Yang's paper on efficient quantum circuit compilation focuses on the pragmatic challenge of implementing complex quantum algorithms on noisy hardware. They propose an approximate method for compiling target circuits into brick wall layouts that can be directly implemented on real quantum computers. Their key innovation is finding ways to maintain the essential dynamics of the original circuit while significantly reducing its depth, which is crucial for execution on noisy hardware. Their experiments on IBM quantum platforms achieved impressive compression rates, 12.5 times for n = 12 qubits, effectively extending what's possible on current devices. Kessin's paper takes a more theoretical approach by introducing a graph-based representation of stabilizer codes, an important class of quantum error correction codes. The innovation here is that this graph representation provides intuition and guidance for constructing and analyzing quantum codes, which traditional stabilizer tableaus don't offer. By establishing a bijection between tableaus and graphs, Kessin provides a universal recipe for code construction. This could significantly impact how we design quantum error correction codes, which are essential for fault-tolerant quantum computing. Hyeok et al. Focus specifically on the design of variational quantum circuits, which are central to many near-term quantum algorithms, VQE. They propose entanglement-informed ansatz schemes that naturally emerge from specific models. Their approach aims to balance accuracy with minimal use of 2-qubit entangling gates, which is crucial because these gates are the most error-prone operations on current hardware. Their detailed analysis across different models provides insights into how to design ansätze based on the expected entanglement structure of the target state. The common thread among these papers is the recognition that naive approaches to quantum circuit design don't work well on real hardware. Each paper proposes a different strategy to make circuits more efficient and error-resistant. Guo and Yang through compression, Kessin through graph-based design principles, and Hyeok et al. Through entanglement-informed construction. Together, they represent a multifaceted approach to the fundamental challenge of bridging the gap between theoretical quantum algorithms and practical implementation on real devices.
That's really helpful in understanding how these different approaches to circuit design complement each other. Shifting topics slightly, I noticed a couple of papers addressing the challenge of estimating quantum computer power and performance. Rodenburg's paper on estimating quantum computer power and Kulkarni et al.'s paper on classical quantum integration seem to be tackling aspects of this. How do these papers contribute to our understanding of quantum computing capabilities?
These two papers address complementary aspects of quantifying and leveraging quantum computing capabilities, though they approach the challenge from different angles. Rodenburg's paper on estimating quantum computer power tackles a fundamental question. How do we quantify the computational capability of a quantum device in a way that's meaningful for end users who may not be quantum experts? The paper shows how to estimate quantum volumetric metrics based on system parameters like qubit number, connectivity, and physical error rates. This is significant because while detailed benchmarking metrics exist, they're often too technical for potential users who simply want to know if a quantum computer is powerful enough for their application. The paper also analyzes how the overhead required for quantum error correction affects metric values for systems below the error correction viability threshold, providing a more realistic picture of practical quantum computing power. Kulkarni et al.'s paper on classical quantum integration focuses on a different but equally important challenge: efficiently interfacing classical data with quantum systems. They recognize that the utility of quantum computing depends not just on the quantum processor itself, but on how effectively we can transform classical information into quantum states for processing. They analyze three prominent encoding models, phase encoding, qubit lattice, and FRQI, to quantify their characteristics and impact on quantum processing workflows. This comparative analysis provides insights into the limitations and potential of different encoding approaches, which is crucial for developing practical quantum computing solutions. Together, these papers contribute to our understanding of quantum computing capabilities in complementary ways. Rodenburg helps us estimate the power of quantum processors themselves, while Kulkarni et al. Help us understand the efficiency of the classical quantum interface, which is often a bottleneck in practical applications. Both aspects are essential for realistically assessing what quantum computers can achieve in practice beyond theoretical qubit counts or gate fidelities.
That makes sense. Both the intrinsic power of the quantum processor and the efficiency of the classical quantum interface are crucial for practical applications. Let's talk about the papers related to software development for quantum computing. Upadhyay et al. Analyze quantum computing repositories, and Ramalho et al. Discuss quantum testing. What insights do these papers provide about the current state of quantum software development?
These papers provide valuable insights into the emerging field of quantum software engineering, highlighting both progress and challenges in this rapidly evolving domain. Upadhyay et al.'s analysis of quantum computing repositories is particularly comprehensive, examining over 21,000 repositories with more than 1.2 million commits from over 10,000 developers. Their findings paint a picture of a rapidly growing community, with a 200% increase in repositories and 150% rise in contributors since 2017. This growth trajectory suggests increasing interest and investment in quantum software development. However, their analysis also reveals potential gaps in software maintenance practices. They found a strong focus on perfective updates, adding new features or improving existing ones, but relatively few corrective commits, suggesting potential challenges in bug resolution. This might indicate that the quantum software ecosystem is still in an exploratory phase where new functionality takes precedence over stability and reliability. Ramalho et al.'s case study on quantum testing complements these findings by examining testing practices in the Qiskit algorithms library. They identified 7 distinct testing patterns, including the use of fixed seeds for randomized algorithms, deterministic oracles, and both precise and approximate assertions. Interestingly, they found a prevalence of classical testing techniques applied to quantum elements, with limited adoption of specialized quantum testing approaches from recent research. Together, these papers suggest that quantum software development is experiencing rapid growth, but is still maturing in terms of software engineering best practices. The community appears to be adapting classical software engineering techniques to quantum contexts, while gradually developing quantum-specific approaches. The papers also highlight the need for specialized tools and improved documentation to support quantum software development. These insights are particularly relevant when considered alongside papers like Kim et al.'s work on human quantum-computer interaction and Meller et al.'s review of programming tools for analog quantum computing. Collectively, they underscore the importance of developing not just quantum hardware and algorithms, but also the software engineering practices and tools necessary to make quantum computing accessible and reliable for broader adoption.
That's fascinating. It sounds like the quantum software development ecosystem is growing rapidly, but still needs to mature in terms of best practices. One last area I'd like to discuss is quantum hardware innovations. Taravati's paper on space-time coupled qubits for enhanced superconducting quantum computing seems particularly interesting. What's novel about this approach, and how might it impact quantum computing hardware development?
Taravati's paper introduces a truly innovative approach to superconducting quantum computing architecture that could address several fundamental limitations of current designs. The key innovation is the use of a space-time modulated, cryogenic-compatible Josephson metasurface to enable what they call polychromatic qubit coupling. In conventional quantum processors, qubits typically interact only with their nearest neighbors, which limits connectivity and requires complex swap operations to enable interactions between distant qubits. These operations increase circuit depth and exacerbate decoherence issues. The proposed metasurface acts as a sophisticated mediator for qubit interactions, transforming nearest neighbor connectivity into all-to-all qubit interactions by facilitating frequency-selective interactions. This is achieved through dynamic four-dimensional wave manipulation, non-reciprocal state transmission, and state-frequency conversion capabilities of the metasurface. What's particularly promising about this approach is that by isolating qubit couplings into distinct spectral channels, the metasurface can mitigate crosstalk and environmental decoherence, potentially extending coherence times and preserving quantum state fidelity. Their simulations and analyses show significant enhancements in connectivity, robustness, and entanglement stability. The impact on quantum hardware development could be substantial. This approach addresses several key bottlenecks in scaling up quantum processors: limited connectivity, susceptibility to noise and crosstalk, and decoherence. If successfully implemented, it could enable larger, more robust quantum processors without requiring the same level of error correction overhead that current architectures demand. This work aligns with other hardware-focused papers this month, such as Shapurian et al.'s work on quantum data center infrastructures, which explores scalable architectural designs for interconnecting multiple quantum processors. Together, these papers suggest that innovative architectural approaches may provide alternative paths to scaling quantum computing beyond the traditional focus on increasing qubit counts and reducing individual gate errors.
Thank you, Bob. This has been an incredibly insightful discussion of January 2025's quantum computing research. It seems like the field is making progress on multiple fronts simultaneously, from hardware innovations and software development practices to practical applications and theoretical advances. What strikes me is the increasing focus on making quantum computing more accessible and practical, whether through better interfaces, hybrid classical quantum approaches, or novel hardware architectures. It feels like we're moving beyond proof-of-concept demonstrations toward more practical implementations that could eventually deliver real-world quantum advantage.
You've captured the essence of this month's research perfectly, Alice. What's particularly encouraging is the convergence of efforts across different aspects of quantum computing. We're seeing hardware innovations that address fundamental limitations, software tools that make quantum programming more accessible, and algorithms that work within the constraints of near-term devices while pointing toward future capabilities. The pragmatism in many of these papers is noteworthy. Researchers are increasingly focused on what works now or in the near term, rather than purely theoretical advantages that might only be realized with perfect fault-tolerant quantum computers. The proliferation of hybrid approaches, whether combining classical and quantum resources or different quantum paradigms like gate-based computing and annealing, reflects this practical mindset. At the same time, foundational work continues on error correction, circuit design, and quantum internet protocols, laying the groundwork for longer-term advances. It's this balance between near-term practicality and long-term vision that makes this an exciting time in quantum computing research. January 25 seems to represent a maturing field that's increasingly focused on delivering practical quantum advantage while continuing to push theoretical boundaries.
Well said, Bob. I think that balance between pragmatism and vision is exactly what the field needs at this stage. Thanks again for sharing your insights on these papers. It's given me a much clearer picture of where quantum computing research stands at the beginning of 2025.